So hi everyone. Can you listen me? It's working? Okay. So means we will keep listening lot of theoretical stuff since 2 days. At least my I've got headache from all these things. So it's a bit different things. Now it's about something about the technology stuff. Maybe you see some beautiful graphics and like these things. So it's Quantum Leap, an introduction to quantum technology. So yes, I am Altaf Nizamani. I'm associate professor at University of St. Jamshedpur, and I am a member, we can say ex-member of IQT group at University of Sussex, Brighton, where we are developing actually quantum computers and quantum sensors using the trapped ions. So I think, so here is our group. Professor Hensinger is our group leader here, and we are all postdocs and undergraduate and graduate students all over there. And most of the fundings comes from UK National Quantum Technology Hub, and they are investing billions of pounds to develop quantum technology and bring these all stuff from the state-of-the-art experiments towards the like for community, for industry, and these things are such kind of, especially for defense and all these other applications over there. So yes, we know that scope of quantum technology. So these technology based off, we all know that based on quantum mechanics, quantum physics, and a lot of far-reaching applications in the field of communication networks and sensors like and quantum metrology, and definitely we are learning here about quantum information technology, quantum information processing, and all these technologies will revolutionize the capacity, sensitivity, and speed of existing devices, or maybe we can see many more new devices in future as well. So lots of government companies are investing, like Microsoft, Google, Intel, IBM, all of these investing huge money to just recap all these potentials. So yes, this is the second quantum revolution, because we know that all existing devices have some quantum technology inside it, like transistor is basically working on quantum mechanics principles. It's not on the classical. The first generation of quantum devices like transistor, like laser, all these working on quantum principles, and a lot of GPS systems we can know about all these things, atomic clocks. So they are like a first revolution. But now we are know more about the quantum mechanics or underlying physics, like we know about the entanglement, about the superposition, about the tunneling of the particles. So all these factors now combine, and now we are ready to like take a second quantum revolution. And under these revolutions, we have a lot of potential, like quantum computing, quantum information technology, quantum sensors, and quantum metrology as well. So yes, quantum computers, you are all aware of this, expect to be able to solve math by even existing supercomputers, or supercomputers of tomorrow can't resolve many problems. Quantum cryptography, this is also emerging field in this here. Quantum sensors, clocks, magnetic sensor, gravitational sensors even are developing under this quantum phenomena. And these have a lot of applications, like in defense, or find underground pipes, and can develop the biomedical imaging devices, and magnetic fields. They can detect underlying pipes, and for many applications like oil reservation applications. So there's a most work is going on to the sensors as well. So yes, I give you a brief idea of the quantum computers and the quantum sensors a bit as well. So what do we need actually physically for these quantum bits? So we know that this should be a quantum system. There's the two-level system, or maybe some this artificial atoms, and there are the many candidates for these qubit parameters. So these are just give an idea. So a lot of things like trapped ions, atoms, cavity QEDs, and there are superconductors over there. G junctions also work as the qubits, and quantum dots, and other like NV centers, diamond, phosphorus atoms in silicon, carbon deficiencies, NV centers. So a lot of candidates are there for qubits, and they have each has some advantages and disadvantages as well. So I will focus on ion traps here, where we are developing quantum computers using these ion traps. So we know that experimentals are worrying about the quantum, how to build a quantum computer, universal quantum computer. Okay, so there's the criteria, and this criteria means that the system should be scalable, physical device, and we have well-defined qubits, because this is the quantum system, it's always a statistical phenomena, so we should be have very, very well-defined qubits over there. And we should initialize them. Decoherence is the problem with the quantum systems, so we should have very long decoherence times, have universal set of quantum gates, have permit high quantum efficiency qubit specific measurements. For example, photonic systems are very long-lived quantum states, but they are not as scalable as solid systems. जिन्हें उनको scalable नहीं कर सकते इस तरह से. So trapped ion. So yes, they are the means they have very good advantage on the other systems as well. Ion traps interact strongly with the Coulomb force, and they can be trapped by electrical or magnetic fields. They have very long coherence time. Their hyper transitions have lifetime of minutes, and even some have very long years, as long as the years. We call them state preparation of these qubits can be done by using optical pumping, using lasers. Measurements also can be done very easily using their fluorescence coming out from the atoms. They have high fidelity gates, 1, 2, 3 qubit gates have been demonstrated, and scalability means people are working, our lab is also working to make the scalable systems. So on one single chip, we can trap 10, 20 ions very easily, but for the computation stuff, we need thousands and millions of qubits. So how we trap ions? So like we apply some electric field over there. Like in this picture, you can see that these red lines and the other black and blue lines. So we apply RF voltage, means like AC voltage here with some frequency associated with them, and then the DC voltage in combination with them to trap ion in all 3 dimensions. So how when we apply RF filter, we can see this kind of potential here, like a saddle type, and because looking at the saddle, you can see that if I can demonstrate in the next slide, it can fall down, but if you rotate this slide, then we will see that we can trap these ions or charge particles. So this is like a saddle trap here, means a simple means it's like a saddle there. So just asking you, if I put a piece of marble over there, would it will stay or it will fall down? If I put a piece of marble or ball over the saddle, what would happen? It will stay there or fall down? Right now it's still.
It's unstable equilibrium.
Okay. So when I just demonstrate this, if we start rotating this, and now if we put a marble over there, and then you can see that it is stay over there. So similarly, if the charge particle is there and we start to rotate this fielding around it, then we can trap the charge particle like in this saddle trap here. So this is also another example. You can see that this is for the demonstration purpose. These are the electrical electrodes are there, and these are the dust particles, simply dust particles. They are trapped, they are charged, and if we fail down these dust particles in this trap, and you can see they are trapped inside this potential. So now scalability, because we can trap these very easily in these between the electrodes, but scalability is a problem. So now similar these traps, which we call in our physics clinics RF Paul traps. So if we make them a surface trap, so these electrodes now on a single layer over there, and then similar fields can be produced by applying RF in the AC voltage over there and the DC fields over there. And from this you can create a potential like here, pseudo potential here, and where is the RF nil over the surface, few micrometers, 10 to 50 or maybe 100 micrometers over the surface, and here is a charge particle, then you can trap these particles for a very, very long time. So there the multiple geometries are there. So in the top slide you can see here, one is the center segmented DC electrodes. These, the black ones, gray ones are RF electrodes. and here are the 6 outer segmented DC electrodes, and center one are the RF potential. In both cases, ions will be trapped in the center above these center electrodes. So how we load ions? So once we have the chip over there, we applied all the appropriate voltages over there, RF and DC voltages, and then we have an atomic flux coming from some oven arrangement. When the atoms come over, I am talking about the ytterbium as an ion we are using. So ytterbium flux atoms are there, and then we apply 2 lasers. It is called photoionization technique. We excite the atom to excited state first, and then another laser bring in, and it will eject the electron from the outer shell and make them charged particle. And all this happens under the vacuum range is very, very, means ultra high vacuum level, we call this, the 10 power minus 11 millibar. So this is the means better vacuum even the space. Okay, so laser cooling. So once we trap the ions, because they have a lot of motional heating and all this stuff, they are not suitable to do any quantum stuff. So first you have to cool them down at milli or even micro Kelvin level. So for this we use laser cooling or Doppler cooling techniques, different multiple lasers from different sides, and using all these lasers, we cool them down in the like to do some quantum stuff here, like 0 state and the 1 state. So we use different lasers like 369 laser, 638 and 638. So different lasers are there. Okay, so once they're trapped, so how we use them as a qubit? So here you can see that so it can be like their hyperfine levels like F0 and F1 state of their ground state, or maybe we use a magnetic field and split these lines into their Zeeman splitting, and we also can use these as a qubit states. And we can see here, I'm just going to slightly introduce here magnetic sensors. So we can see that these levels are sensitive to the applied B field. And whenever the B field, if you measure these transitions very accurately, then we can deduce what the B field is there. So they can work as a magnetic sensor as well. So state preparation means first we prepare ion in a very well defined. This is the condition for do any practical quantum stuff there. So we turn on lasers and their side bands to cool the atoms to ground state. Like here you can see all these blue are like transitions over there. So we excite from the ground state S to P state, and then ions will fall in the 0 state. So within a few milliseconds or less than a millisecond time, all these states are populated here in the 0 state. So ion will stay there because this is hyperfine. So atom or ions will be remain here for longer times here. So once it is a state preparation, then we detect either ion is in 0 state or 1 state. We turn off all these side bands, and only one particular transition here we can see that if the light is coming out from the atom, it means the ion is here, state 1, and we call it bright ion. If there's no light coming out from the atom, photons coming out of the atom, we can say that the ion is in the 0 state. So here we make a histogram of these photons, means collection of photons. So if the 0 means the ion is dark, F0 state. If it is emitting fluorescence from it, so we can see that number of photons are there, it means it is in the F1 state. So means we can very accurately initialize the system in 0 state or in 1 state, depending what do we want. So in practically means how these systems look like. This is a vacuum chamber, like football size chamber there. So a lot of electronics going in to apply RF and DC voltages, a lot of wiring there. These are the ovens to generate flux. And when this whole system is here, and you need lot of pumps to create a vacuum inside it. Because I told you that we need an ultra high vacuum, 10 power minus 11 millibar. So it's a very high level of vacuum there. So this is the trap here. So these are the electrodes where we apply DC voltages, RF voltages here, and this region in the center of there, we ionize the atoms, and once they are trapped, they are shining like here. So this is the 5 micrometer level. So you can see the ytterbium crystal, means they're all individual atoms, single atoms. So overall means experimental setup looks like this. Lab, you can see a lot of stuff over there, even under the table, over the table, and other rooms are also there. So just trap few ions, few 10 or 20 ions. So means we cannot make a quantum computer using this existing technology in this way. Because imagine this is for 10 items. So you need, for example, millions of qubits, then what will be the scalability of this level? So yes, now the quantum abyss is what? Means state of the art experiment, which I just explained 20. And quantum bits are this 20, and you can see useful computer, you need thousands of such qubits. Similarly, 100 logic gates can be in a state of art experiment, you need means millions and billions of these things. And other stuffs also there for quantum, real quantum computing, information technology. Noise is the problem, new technology required, error correction is also the problem. So all these new algorithms are required. So scalability, we in our lab, we are taking the scalability issue there. What we do is we're using existing microfabrication technology to make very surface traps like this. And when we combine all these traps, then you can trap as many as ions you can, like millions of ions you can trap in different chips. And they need to be shuttled around there. You need AC and DC voltage controls. So this is an example, means how these chips would look like. So this is also the demonstration of chips. You can see this is a single zone here. You can see we trap loading zone first. We trap ion here, then shuttle them for the gate operation, for the memory stuff. And the combination of these junctions, you can see you can make a one module there, and you need hundreds of modules to trap many ions. And readout can be done because in the previous experiments we use means a very big cameras, EMC CD cameras, but here for this setup we want to detect exactly underneath it because there are central electrodes there. So one of these can be used as a silicon photodetector, which can detect for measurement and for state preparation purpose. So means how to construct a microwave trapped ion quantum computer. So in this video should be, so this is now scalability. So now this is the one trap here, loading zones, entanglement zones. So once we trap ions, and then we shuttle across the junction in the entanglement zone, and then so underlying other stuff is there. So we use microwave radiation to excite and de-excite atoms. So now we can shuttle them in different zones like this here. So readout can be done using lasers. So if we shine the laser over there, so fluorescence can be generated, detect the position. It's in F0 state or F1 state. So once it's done, so this is like a one module, and you can see simultaneously it's happening in all other zones as well. So once this, put this in a vacuum chamber and steel mag chamber over there. So then another modules are coming in, and we have to shuttle around the ions from one module to other module as well. So there's the gap between them, and this can be adjusted by actuators, piezoelectric actuators over there, so that ions can easily move from one surface to other surface like this. So now these are stabilized, and now you can see ions can move from one module to the other module. And similar, just repetition of all these things can make a big module. It's all under vacuum. And then we repeat all these setup. So multiple connections, all systems come together. So it's like means overall football size ground. to cover all these modules over there. So this design is now actually published in the Nature Science journal last year. Okay, so that was about the quantum computers. So now about quantum sensors. This means we can say spill out from the quantum technology devices. I told you earlier these qubits are sensitive to the B field. So once you measure the transitions accurately, you can know what the B field is very accurately. Okay, so similarly, you can see these are the sensitive transition of ytterbium or any trapped ion. So if you measure these accurately, you can know what the field is this, and how accurately we can measure. So these trapped ion magnetometers have means ultra high sensitivity in picotesla. Just compare this. Earth's magnetic field is 0.5 millitesla, means 500 microtesla, and this is in the pico region. So means millions times smaller field than the Earth's magnetic field. And they can use the gaugeometer because they can see means the difference in the magnetic field across the layers, and they can detect means radio frequency range means oscillating magnetic field as well from 100 kilohertz to tens of megahertz, or they can work as a lock-in feature. If you interested in a particular signal, then we can lock our ion trap for a particular frequency, and it can detect it only to avoid any surrounding noise. And they can work without magnetic shielding, operate in room temperature, because existing I would say super sensors or magnetometer work at using superconductors, and you know that superconductors required means a very low temperature level of 4 Kelvin or helium level cooling. Another thing is here, just I missed it, can be converted into atomic clock. So these ion trapped are means at the time, even today I was reading the news that in NIST they have developed ion based atomic clock, which has accuracy 1 into 10 power 18 times. So means our universe would be end, but it won't gain more than second. Even the universe time has passed. So atomic clocks can be made using these ion traps. And this is then just comparison with different magnetometers. So traps, you can see that even they can detect particular gigahertz range frequencies. So microwave also can be detected using these trapped ions. So this is the quantum technologies timeline. This is I took this from the European Union's means current portfolio thing. They are also investing hundreds of means millions of euros for the future quantum technologies, and this is they have proposed this timeline. You can see atomic clocks. They are making these clocks. I told you today that they have means super stable atomic clock. And quantum sensor, this is the new thing which is coming in a couple of years. Then quantum intercity quantum links, quantum simulators, and then you see the timeline for the quantum computer. So it is about 2035 like this. And for this.